Okay, this is a video lecture for Math 283, and the topic is the cross product. Now, we've already talked about the dot product, which is one way you can multiply two vectors together, and the result of the dot product is a scalar, it's just a number. It turns out there's another way we can multiply two vectors together, and that's called the cross product. With the cross product, the result of that is another vector, not a number. Before we talk about the definition of the cross product, let's first talk about determinants. And if we have a 2 by 2 matrix, A1, A2, B1, B2, the way we calculate the determinant of this matrix is we cross multiply and subtract. So we get A1, B2 minus A2, B1. Okay, let's do an example of this. So let's suppose we had 1, 2, 3, 4, and we wish to calculate the determinant of that. We'd cross multiply, so we get 4 minus 3 times 2 minus 6, okay, and that gives us minus 2. Now we can also have the determinant of a 3 by 3 matrix. So if this is our 3 by 3 matrix, A1, A2, A3, B1, B2, B3, C1, C2, C3, and we want to calculate the determinant of that. The way we do that is we take A1 times the matrix, determinant of the matrix B2, B3, C2, C3, minus A2 times B1, B3, C1, C3, plus A3 times B1, B2, C1, C2. Okay, and what's the methodology here? Well, we start with this top number here times the determinant. Now, the way we determine the determinant, or the matrix we're taking the determinant of, is we can draw a line across like this and a line like this. For this particular, for the first term, we're left with this determinant, with this matrix. So that's what we put here. The next term, we have to include a minus sign. We take this next term, A2, and then we could create lines like this, and whatever numbers are left over go in our second matrix, and so on. So hopefully that pattern makes sense to you guys. Let's do an example. Let's calculate a determinant here, a 3 by 3 determinant as an example. So let's do this. Let's calculate this determinant. 1, 2, 4, minus 3, 3, 1. 3 minus 2, 5. The determinant of this matrix will be 1 times 3, 1, minus 2, 5, minus 2 times minus 3, 1, 3, 5, plus 4 times minus 3, 3, 3, minus 2. Okay. And then we can multiply these out, and this gives us 15, excuse me, I got something in my throat, 15 minus 2 times 1, okay, and the second one comes out to minus 2 times minus 3 times 5 is minus 15. I'm just going to make this shorthand here. This is minus 2 times 1 is minus 2, but that, now we subtract that off, so we get a plus 2. This is minus 15, minus 3, okay? And the third term is, shoot, that should have been minus there. The third term is 4 times, minus 3 times minus 2 is 6, and then minus 3 times 3 is 9. So this is what we get. And then we can simplify this. This is 17. This is minus 18 times minus 2 is 36, and this comes out to 4 times minus 3 is minus 12. And if you guys add these together, this comes out to 41. So that's an example of calculating the determinant of a 3 by 3 matrix. Okay, now why is this important? This is important because the cross product is defined as being the determinant of a particular 3 by 3 matrix. So let's write that down here. If we have two vectors, and one vector A is equal to A1I plus A2J plus A3K. And the second vector B is equal to B1I plus B2J plus B3K. Those are our two vectors. Now we want to take the cross product. The cross product is defined as the determinant of this 3 by 3 matrix, I, J, K, A1, A2, A3, B1, B2, B3. And we can write this in terms of 2 by 2 matrices. This is I times A2, A3, B2, B3, minus J times A1, A3, B1, B3, plus K times A1, A2, B1, B2. So this is the definition of the cross product. Now why don't we do an example of this? So if we have these two vectors, let's suppose we have A equals 1, 2, 3, and B equals 4, 5, 6. Let's calculate the cross product of these vectors. A cross B will be equal to I, J, K, 1, 2, 3, 4, 5, 6. And we can write this out as 2, 3, 5, 6 times I minus 1, 3, 4, 6 times J plus 1, 2, 4, 5 times K. And now we have to calculate this. If we cross multiply, we get 12 minus 15I minus 6 minus 12J plus 5 minus 8K. And if we simplify this, this is minus 3I plus 6J minus 3K. So that's an example problem of calculating the cross product of two vectors. Okay, let's talk about some properties of the cross product, some important properties of the cross product. Sorry, I erased that example. I was going to use that result. Let's see if I can remember that result. Let's write this down. A equals, what was it? 1, 2, 3. B equals 4, 5, 6. And we found the cross product. A cross B equals minus 3I plus 6J minus 3K. I'm going to use that in another example here. Talking about properties of the cross product, one important property is the cross product of A cross B is perpendicular to both vectors A and B. Okay, so the cross product of any two vectors is perpendicular to those two vectors. Now the book has a proof of this. I'm not going to go through the proof, but with this example, what I would like to do is show this is true for this example. So what I'm going to do is take the dot product of vector A with the cross product of A cross B. Okay. Now, if these two vectors, if this is indeed true, that A is perpendicular to A cross B, then the dot product of A with A cross B should be 0, because two vectors that are perpendicular have a 0 dot product. If you guys remember that, that they're orthogonal, and that's because there's a cosine theta term in the dot product. So let's see if this is true. This is going to be 1, 2, 3, dotted with minus 3, 6, minus 3. Okay, and if we do that, we get minus 3 is the first term, the second term is plus 12, and the third term is minus 9. And this adds to 0, so indeed that's true. And if you guys want, I'm not going to do this, you also could check that B is perpendicular to A cross B. So that's an important property of the cross product. It's perpendicular to both the vectors involved. Another important property of the cross product is that if you take the cross product of a vector with itself, you get 0. Okay, the cross product of a vector with itself is 0. And another important property is that A cross B, if you flip the order here, it changes it to with a minus sign. So if you reverse the order of the cross product, you have to add a minus sign on. Now, I want to talk a little bit about the right-hand rule. So the cross product is perpendicular to these two vectors, but what direction does it point? Well, let's say we had a vector A pointing this way, and we have another vector B pointing this way. Okay, and we take the cross product of A cross B. There's actually two possible ways that the cross product could point. It could point straight up or straight down, just so long as it's perpendicular to both A and B. Okay, how do we know which way it points? Well, there's a right-hand rule for cross products. Okay, and the right-hand rule says that what you do is you place your fingers in the direction of A, you curl them in the direction of B, and your thumb will point in the direction of the cross product. So in this case, the cross product will point up like this. So this would be A cross B. So that's the right-hand rule. And keep in mind, these two vectors are not necessarily perpendicular, but this vector is perpendicular to both of these vectors. Okay, I'm going to stop the video now and come back for another quick video. I'm going to do this video in two parts. I'm going to consider an important theorem, and then also I'll consider some applications to parallelograms.